Hello everyone, my name is Daryosh Vatanparvar. I'm from Microsystems Lab, University of California, Irvine, and today we're going to present the results on how electrostatic frequency tuning can potentially cause instabilities in Coriolis Vibratory Gyroscopes. Let's start off by explaining what a Coriolis Vibratory Gyroscope is. So a gyroscope is essentially a 2-degree of freedom resonator in which the proof mass can freely oscillate along two orthogonal axes. In an ideal case, by operating a gyro in the open loop angular rate measurement mode, the drive mode is excited at the resonant frequency and the vibration amplitude is sustained at a set value. By applying rotation to the sensor due to the Coriolis coupling, the sense mode would be also excited, and it can be shown that the vibration amplitude along the sense mode is proportional to the angular rate of the rotation which is applied. In the non-ideal case, however, we would end up with energy dissipation mechanisms, but also we would end up with imbalance in stiffness. Imbalance in stiffness means that the resonant frequency along the drive mode would not be identical to the resonant frequency along the sense mode. Imbalance in stiffness is caused by fabrication imperfections and isotropic mechanical properties of material which is used to fabricate the resonators, but it also can be caused by residual stress due to packaging of the sensors. These non-idealities cause the oscillation pattern, as shown for the ideal case in the previous slide, to deviate. And in context of sensitivity, imbalanced stiffness causes a degradation in sensitivity. When we talk about miniaturization and going to smaller gyroscopes, we're essentially limiting ourselves to smaller drive amplitudes, but also due to poor tolerances of microfabrication, we would end up with high frequency splits, meaning that the sensitivity of these sensors would degrade. However, to compensate for asymmetries and imbalance of stiffness, one way is to use electrostatic frequency tuning. In capacitive MEMS gyroscopes like the DFP, which is shown here, periplate electrodes are embedded in the design, which can be used to regulate the resonant frequency along an intended axis. Assuming that the resonant frequency along x-axis is higher than the resonant frequency along the y-axis, by applying a DC voltage across periplate electrodes along x-axis, electrostatic spring effect is created with a negative stiffness, meaning that the resonant frequency along x-axis can be reduced. By tuning the DC voltage, the two resonant frequencies can be matched. We're illustrating how electrostatic frequency tuning works in this figure. On the horizontal axis, we have the tuning voltage, which is applied along x-axis, and on the vertical axis, we have the resonant frequency. As you can see, at zero tuning voltage, we have a resonant frequency split on the order of 112 Hz, which corresponds to the as-fabricated frequency split. But as we increase the tuning voltage, a quadratic reduction in the resonant frequency along the x-axis is observed. And around 6.4 volts, by applying 6.4 volts tuning voltage, we're able to reduce the frequency split to a value less than 100 millihertz in order to improve the sensitivity. Let's look how the noise performance changes at different frequency splits. One of the major noise sources in gyroscope is the noise created due to the pickup of electronics components. And the equation of the white noise, which is characterized using the angle random walk in the output of a gyroscope, is shown here. As you can see, the angle random walk is correlated to the frequency split, and the behavior is shown on the figure on the left. As we go to lower frequency splits, the angle random walk due to pickup electronics noise, which is shown using the green line, reduces, and we can reach the fundamental noise limit of the Coriolis Vibratory Gyroscope, which is limited by mechanical thermal noise. However, when we look at experimental data, which is shown using the red dotted points, we see that the noise performance only improves down to a frequency split on the order of 1 Hz, and at lower frequency splits, the noise performance degrades. In a recent publication, we were able to identify the cause of this degradation and identify quadrature noise to be another noise source causing this noise performance degradation. Quadrature noise, we were able to show that it's proportional to the resonant frequency noise or the frequency noise of oscillation along the drive axis of a gyroscope. In this paper, we want to understand the contribution of the nonlinearity caused by electrostatic frequency tuning and its contribution to frequency noise, which would be causing quadrature noise in gyroscopes. Let's look more into details of how electrostatic frequency tuning works. So here we are showing a schematic of a single degree of freedom resonator which captures the behavior of a gyroscope along the drive mode. We have parallel electrodes which are biased using an AC and DC voltage for a push-pull drive architecture, and we can show that the vibration, the equation of motion, vibration along x-axis or the drive axis, can be represented using this differential equation. X in this differential equation is the displacement normalized to the capacitive gap size G, and mu x and omega x are the coefficient of damping and the resonant frequency. Based on the equations derived in the paper, which you can find, we showed that the resonant frequency is a function of the mechanical spring stiffness, omega x naught, but also is a function of Kex, which is this electrostatic spring stiffness. As you can see, Kex is a function of the DC tuning voltage, but also it consists of a series of terms. It's shown that the first term is independent of the vibration amplitude, and it can cause a reduction in resonant frequency as shown in the picture on the top. However, the higher order nonlinear terms cause a reduction of the resonant frequency, which is coupled to the vibration amplitude X and A, and this is referred to as the electrostatic softening effect. Therefore, due to electrostatic frequency tuning, the nonlinearity causes a coupling between the amplitude, and as we go to higher amplitudes, the resonant frequency would shift to lower values. Here we want to validate the model which was presented in previous slide. So we measured the resonant frequency along the drive axis of the DFP using a phase lock loop at different vibration amplitudes, and it's shown using the red dotted points. And we included in this figure 3 different models: the Dauphin nonlinearity or the cubic nonlinearity model, the quintic nonlinearity model, which also includes a third order, but also we are showing the model which was presented in this paper using the dashed black line. As you can see, the Dauphin nonlinearity model and the quintic nonlinearity model do not capture the variations of resonant frequency at higher vibration amplitudes because they're in the assumption they're neglecting the higher nonlinear terms. However, the model which was presented in this paper can accurately predict the variations in resonant frequency at the condition of applying 5-volt DC tuning voltage up to a vibration amplitude of 0.8 as shown here. Therefore, we confirmed that the amplitude frequency coupling is substantially large, but also it's a function of the tuning voltage, and it increases with the higher tuning voltage, and also it increases with the vibration amplitude. Now let's look how amplitude frequency coupling results in frequency stabilities. Here I'm showing the control architecture which is used along the drive axis of a gyroscope. HG represents the transfer function along the drive axis. A PLL, a phase lock loop, and a PI controller are used to track the resonant frequency and maintain the vibration amplitude using the in-phase and quadrature phase demodulated outputs of the signal along the drive axis. In this experiment, we recorded the resonant frequency which was tracked using the PLL for 2 hours, and we changed the tuning voltage along the drive axis to see how it affects the noise characteristics. Here we are showing the data. Basically, we use the root power spectrum density of frequency noise at different frequency spectrums. When you look at the frequency tracking bandwidth of the PLL, you see that there is a white frequency noise and also there is a frequency random walk. We were able to show that this noise and frequency correlates to the vibration amplitude noise. Basically, the frequency white noise is due to a noise and vibration amplitude caused by the white noise in pickoff electronics, and the drift or the frequency random walk is caused by a drift in the pickoff electronics gain, causing instabilities in the vibration amplitude. Therefore, we confirm that even by using a PI controller to sustain the vibration amplitude, however, due to the noise and instabilities in vibration amplitude, noise would be translated to the resonant frequency, and as we showed before, this would cause noise performance degradation in the gyroscope. Now let's look how the vibration amplitude along the drive axis affects the frequency noise. As it was explained in the early slides, we said that in order to improve sensitivity, we need large vibration amplitudes. However, as is explained here, a large vibration amplitude would also increase the noise and the resonant frequency along the drive axis. An equation is presented in the paper, lambda, which shows how the frequency noise along the drive axis correlates to the vibration amplitude and the behavior is shown using this plot. You can see that as we go from vibration amplitudes around 10% of the capacitive gap size up to 90% of the capacitive gap size, the noise in the resonant frequency would increase by orders of magnitude. Now, just to confirm this, in an experiment, we characterized the noise output of the DFB gyroscope in two different conditions. In one condition, we were operating the vibration amplitude at half of the capacitive gap size, and in the second experiment, we reduced the vibration amplitude to 10% of the capacitive gap size. As you can see, even though we reduced the vibration amplitude along the drive axis, the noise performance improved, and this confirms that since at lower vibration amplitudes, we would have lower amplitude frequency coupling and improved frequency noise, therefore a lower quadrature noise would appear on the output of the gyroscope. Now to conclude, we demonstrated that even though the electrostatic frequency tuning is an effective way to reduce asymmetries in gyroscope, however, it results in substantially large amplitude frequency coupling. We showed that the amplitude frequency coupling degrades the noise and frequency of oscillation along the drive axis, and this frequency noise results in quadrature noise and gyroscope output. We also demonstrated that the trade-off exists between mode matching in the gyroscope or maximizing the vibration amplitude in order to improve the sensitivity. In the end, I want to acknowledge the funding which was received by DARPA, which made all this research possible. I want to also acknowledge and mention that devices which were used in these experiments were designed and characterized at Microsystems Lab, University of California, Irvine, and they were fabricated as part of the EPC run at Microstructures and Sensors Lab, Stanford University. Thank you for listening, and I would be happy to answer your questions.